We hear about AI, ChatGPT, and large language models literally all the time now, right? But how often do we actually stop and look under the hood? Well, welcome to this explainer. Our goal today is to completely demystify the engine that's driving today's AI revolution. We're going to break down exactly what these models are, how they're built from the ground up, and, maybe the coolest part, the surprising mysteries that still completely baffle the very scientists who created them.
You know that feeling when you first used a modern AI and it just felt almost magical, like it was actually thinking? Well, you absolutely aren't alone. Take a look at this quote from Percy Lang, a really prominent researcher over at Stanford. He openly admits that the AI community itself was caught totally by surprise. They trained these models with the simple goal of predicting the next word in a sentence, and suddenly, out of nowhere, these things can answer complex logic questions, translate languages, and even write computer code. It was a massive shock to the system. So, to figure out why this happened, we need to take a quick look at how AI actually evolved.
All right, to understand why researchers were so shocked, we've got to look at the two main eras of modern language models. And it really all comes down to what they were built to do. On one side, we have PLMs, or pre-trained language models, and on the other side, LLMs, or large language models. These acronyms get thrown around constantly, but the difference between them is literally the key to understanding this entire AI boom. So, think of a PLM, like the famous BERT model from the older era, as a highly specialized worker. The way BERT worked was super focused. Researchers would pre-train it on a massive amount of raw text, but then they'd explicitly fine-tune it for just one specific task. Maybe that was identifying spam emails, or maybe translating English to French. But the crucial takeaway here is that it was a total one-trick pony. If you wanted it to do something else, you basically had to build a whole new model from scratch.
Now, contrast that with modern large language models like the GPT series. The formula just completely changed. Instead of painstakingly fine-tuning for one tiny specific task, researchers said, what if we just take the pre-training phase and scale it up massively? We're talking way more data, way more computing power, exponentially larger models. And the result? An absolute explosion of general multi-purpose abilities. A single LLM can translate, summarize, and code all right out of the box. But how? What is actually happening inside the machine?
To answer that, we have to ground ourselves by asking a deceptively simple question. How does a model actually guess the next word? Because fundamentally, if you strip away the poetry and the coding and the conversational charm, that is exactly what these models are built to do. At their core, they are just next word prediction engines.
Okay, please don't let the math here intimidate you. What we're looking at is a neuroprobabilistic language model. The really important thing to grasp here is that an AI doesn't think in English or French or code, it thinks in probabilities. It looks at the words that came before, compresses all that context into mathematical representations, and then calculates the statistical probability of literally every possible word that could come next. It's essentially this giant complex calculator weighing its options based on patterns it saw in its training data.
And guys, this brings us to the real plot twist of this whole explainer. If LLMs are just doing the exact same probability math as those older, simpler models, why are they suddenly so incredibly smart? The answer is emergence. As physicist Philip Anderson defined it way back in 1972, emergence is when quantitative changes in a system result in qualitative changes in behavior. In plain English, when you take that exact same simple math and scale it up to an astronomically large size, the system stops just predicting words and starts showing entirely new complex behaviors that nobody ever programmed into it.
You can actually see this breathtaking phenomenon happen right here. Just look at the data for tasks like modular arithmetic or transliteration. Notice how the smaller models are basically flatlining at 0% accuracy. They completely bomb the test. But as the scale increases, boom, suddenly, almost instantaneously, the accuracy spikes. The ability literally emerges out of nowhere for no other reason than the fact that the model just got bigger.
So why does this happen? Well, that is the million-dollar question, isn't it? The scientific community still only has competing hypotheses. Is the model somehow implicitly identifying the task? Is it doing some kind of hidden Bayesian inference in the background? Is it learning in real time without actually updating its internal parameters? Or, as some researchers jokingly put it, is it just pure magic? The crazy truth is, we know for a fact that scaling up creates these emergent abilities, but the exact mechanical why is still a massive open mystery in computer science. And we actually tap into this emergence in our everyday use right now. Think about standard prompting. Asking a complex math question directly often causes the model to just output a totally wrong answer. But look at chain of thought prompting. By simply asking the model to show its work step by step, it suddenly nails the right answer. This ability to reason sequentially, that wasn't explicitly programmed into the model. It's an emergent property of its massive scale that we discovered we could unlock just by changing how we chat with it.
All right, let's shift gears from the theoretical magic and step onto the factory floor. How do you actually build one of these massive AI engines in the real world? It basically happens in 3 grueling, highly practical steps: data preparation, pre-training, and finally, fine-tuning and alignment. And let me tell you, those first 2 steps alone are an absolutely monumental undertaking of engineering.
It all starts with the recipe, and the ingredients require a scale of data that's hard to even wrap your head around. Looking at a typical dataset mixture, we are talking about hundreds of billions of tokens, which are essentially fragments of words. As you can see, the model is fed almost 880 billion tokens scraped from the web, over 62 billion from computer code on GitHub, and 65 billion from books. And notice that Wikipedia is actually a tiny fraction of the pie. The model literally needs to read a massive cross-section of all human knowledge just to learn the basic patterns of our world.
But here's the catch. You can't just take the raw, unfiltered internet, dump it into a language model, and expect good results. I mean, the internet is a messy place. Data engineers have to build this grueling filtering pipeline just to process that web data. They run URL filtering, text extraction, language identification, and aggressive deduplication. A massive percentage of the raw data gets thrown out entirely just to guarantee the model is learning from high-quality text.
And getting that pristine, high-quality data matters so much because of something called scaling laws. As we can see here, there's a fundamental rule in AI right now. To drive down the error rate, what they call test loss, you have to push the limits of 3 things simultaneously. You need more compute power, a bigger data set, and a higher number of parameters in the model. If you want a smarter AI, you've got to aggressively scale up all 3 of these pillars at the same time.
So, what does scaling up those 3 pillars actually cost in the real world? Try $2 million. Yep, that is the estimated cost in raw compute power alone just to pre-train a modern 70 billion parameter model like Meta's Llama 2. To pull that off, you need something like 6,000 high-end graphic processing units running red-hot, non-stop for 12 days straight. This isn't exactly a project you can just build in your garage anymore. This requires massive grid infrastructure and some serious financial backing.
And you know, these models have a stark physical reality to them too. Once that $2 million training run is finally over, a 70 billion parameter model takes up roughly 140 gigabytes of hard drive space just to store its parameters on disk. That is highly compressed digital knowledge taking up real physical space on a server rack somewhere.
Which brings us to a major reality check. Building and maintaining these models is fraught with massive challenges. Data engineers constantly have to worry about temporal shift, meaning as the real world changes and evolves, a model trained on older data actually degrades and becomes less useful over time. They're also constantly battling the risk of toxic outputs, because remember, the model learned from the internet, warts and all. And as researchers are quick to point out, there is no magical one-size-fits-all filtering solution here. It requires constant, relentless tweaking and iteration. And that leaves us with a truly fascinating and maybe a little provocative final thought. We've seen that the magic of large language models, that incredible emergence of new abilities, came entirely from scaling up the data, the parameters, and the compute. But the amount of high-quality human text on the internet is finite. So what happens when we literally run out of new books, code, and articles to feed it? Will the emergence just stop? Or are we going to have to find an entirely new way to keep pushing the boundaries? It's a massive question, and it's one the brightest minds in AI are scrambling to answer right now.